Today, inshallah, we are going to continue working in a mechanism. So today we are going to learn how to build a full mechanism. We will use a crank slider mechanism, this simple mechanism, a crank slider that is doing a certain function. We will explain this in details. So we'll include links to define the geometry of the crank and connecting rod, and also are going to include a cylinder to define the geometry of the specimen and the slider. In order to improve the graphics, we are going to use some graphics operations that will enhance the shape of your and the presentation of your geometry in Adams. So look at some operations like subtraction, chamfering, and creating a boss. We are going also to look on creating revolute joint and the prismatic joint. We will make sure that our axis of the prismatic joint or translational joint is correct, because if we don't have this correct, the mechanism will not move. We'll talk about the spring element. How can we add a spring element and what are the properties of the spring element? And then we'll talk about assembly of the system. We will add a motion driver, so we can drive the crank at certain speed. So we'll add a rotational motion driver, and we'll learn about something called function builder and step function input. Of course, we are going to do some pre and post processing for us. So the model that we are going to build actually resembles certain industrial operation. Maybe you have studied or learned about the mechanical press. The mechanical press, one of the designs of the mechanical press is that you have a crank, and this crank is connecting to a connecting rod. The connecting rod will have a punch or cutting tool. This cutting tool or the punch will move against a specimen. So it can bend this specimen, it can create a hole in the specimen, it can stamp the specimen or anything like that. The way we are going to model the specimen, we are going just to model it as this slider element that is supported by a stiff spring. And we are going to select the spring such that it's going to return this specimen back. So when this crank slider, moves due to the effect of the input motion, the piston is going to contact this specimen, and as it pushes the specimen, it will create something like, in real life, it will be something like bending or piercing or stamping. The way we are going to model the resistance is using this spring. The way we are going to model the contact between the specimen and the tool is using contact force element. We will drive the crank with a motion, so we'll learn how to define a motion in our system. So if I look at the model, we are going to define or model our. So if I'm going to explain the components of this model. We are going to model the system as a link representing the crank. Link number 2 will represent the connecting rod. Link number 2 is going to have length equal to 10 centimeters. So this length AO2 is going to have a length of 10 centimeters. The length of the connecting rod will have length 20 centimeters. The slider is going to be modeled as a cylinder with length 5 centimeters and radius 5 centimeters also. The specimen is going to be modeled as a cylinder with 5 centimeters and radius 5 centimeters. As you remember, when we talked about the cylinder is typically defined by two parameters: the length of the cylinder and the radius of our cylinder. In order to define the direction of the cylinder, we usually define a marker at the base. So we'll identify a marker to define the location of the center of the base, and then define the extent or the length of our cylinder, the height of the cylinder, and the radius of the cylinder. We are going to model the piston and the specimen using those two cylinders. One way to start modeling a system is to draw a small sketch like this. So we can identify how this simple mechanism will look like from the initial conditions. So I can start with the origin of our O2, the origin of the mechanism O2. If we assume the crank slider will be extended, so we have A will be located on the horizontal x-axis at 10 centimeters, B will be located at 20 centimeters, and C is going to be located at distance from B equal to half of this cylinder and this cylinder. And then the spring will have, we assume the spring will have length of 20 centimeters. Now, in order to define those components in the Adams environment, I need to identify some kind of points where I'm going to attach those elements. For example, if I'm going to assume our mechanism is going to be in this in this position, how are we going to create the condition, the position of the cylinder, this cylinder and this cylinder? This is one condition for our mechanism. But as you can see, in this condition, the spring will be compressed. We don't know how much force are we going to have in the spring while it is compressed. So instead of drawing the mechanism at this position, it will be much easier if we draw the mechanism when the crank is starting in the top position, such that our spring will not be compressed. So in order to do this, I'm going to draw this mechanism and the new position. So I'm going to start my origin O right here. Our crank has length of 10 centimeters, so this is O2. Assume this will be at the global origin. So I'm going to define point A at this position. At this position it will be at minus 100x, 0y and 0z. And then I will define point B. If the crank is at this position, then we are going to have the connecting rod coincident with it, but it will be in the opposite direction. So this will be point B. The location of point B will be also at 100 and 0, 0. Now, as you can see, this point B is the center of this slider, which means we are going to draw our first cylinder at this position, like this. If this is our first cylinder, this means we need to define the marker right here. So this marker defines the base of this cylinder. So I'm going to call this marker M1, and this position from here to here is half of the length of the cylinder. So this is 2 centimeters. So the distance from O2 to this M1 will be 7.5 centimeters, which we can say it's 75 millimeters, like this, 0x, 0y. We are going to assume the second cylinder will be located like this, such that the piston or the slider is going to contact it. So we will assume this cylinder is going to have a marker to define the center, the base of this cylinder, and we'll call it M2. Now, the distance from here, the location here is 100 millimeters. And notice also the length of the crank is 100 millimeters. So the total deflection that you are going to take from the crank is equal to 100 millimeters. So I'm going to assume that the distance from this point to this point is 5 centimeters. 5. So the location of this marker will be at 150, 0, 0. Now the spring, we are going to assume the spring is attached in the middle here, in the middle of the piston, at the middle of the specimen. We are going to have the spring. So this is going to be located, the center will be located at 175 millimeters, and this will be the other end of the spring. This will be, the spring length is 20, so we'll add 20 to this. So this will be 37500. So what I'm going to do in atoms, I'm going to start by creating those points. Point A, this is number 1. Point B, number 2. Point M1. Point M2. And point S1. Those 5 points, I'm going to create them, and based on them I'm going to create my geometries. So now what I'm going to do, I'm going to start working in atoms. So I will run atoms and start a new model. So this is our atoms here. We're going to start a new model. New model. I'm going to start by defining the directory where I'm going to save my files. So this is where I have my models in A343. This is my folder, and I'm going to call this model mechanical press. Mechanical underscore press. We will leave the units and we will leave the direction of the gravity as is, and I will click OK. As you can see, I have no bodies, I have no connectors, no motion, no forces, nothing yet. So we're going to start by adding our points, our hard points. How do I add point? I can go to this bodies tab. Under construction, I'm going to select points, geometry points. So I'm going to click over here and I'm going to select add to ground. Now I'm going to select, I would like to enter the coordinates of point A. In order to enter the coordinates, I'm going to right click. It will open the event location, as you can see. So I'm going to select this point at minus 100x, 0y and 0z. So again we will right click, it will give us the location event. I'm going to edit the coordinates as minus 100x, 0y, 0z, and click apply. As you can see, the point is created, and you can see those hashed lines represent they are on the ground. So I'm going to go to the ground and change the name. Instead of point 1, I'm going to call it point A, like this. Now I'm going to create point B. So I'm going to add again construction point on the ground, right click and select the coordinates. The coordinates of point B are located at 75x, 0y and 0z. And I'm going to rename this point as point P, like this. I did a mistake in defining the coordinates of point B. point B actually should be located at 100, not 75. So how do I change the coordinates of point B? I can right click on point B and select modify. Actually it gives me this very nice window that I can use to edit the location of the different points. So as you can see here, I can see a table. This is the point name and the coordinates x, y, and z. So A is correct, as we defined before. A is located at -100, x, 0, y, and 0, z. B should be located at 100. So I can click on the cell and edit the cell. So it will be 100 in the x, 0 in y, and 0 in z. Now if you click apply, Adams should move this point forward like this. So now if I click apply, see what happened? It moved the point. Also I can create new points here. So let me create M1 as well, because I would like to create the point M1. How can we add a new point? I can click on create. Now you see the point 3 is created. So I would like to rename this point. How do I rename this? Change the coordinates of this point. I can click on X, enter 75, and then 0y, 0z. I would like also to create M2. So I'm going to call create point. So I'm going to change the position of M1 and click apply. Once we create a point, it is created here. I'm going to create a new point for M2. So I'm going to create M2 located at 150 in X, 0 in Y, and 0 in Z. Now if I click apply, it will create the point for me like this. Also I'm going to create the last point, which is S. So I'm going to click on create. Now I'm going to have the coordinates of point S, 375, and click apply. Now I created all the points that I need. I'm going to click OK. But see, I have the names here. I would like to change those names. So this is point 3. I'm going to call it M1. And point 4, I'm going to call it M2. And point 5, I'm going to call it S1. Again, if you would like to see the coordinates, right click on any point and select modify. It will show you the coordinates of the points as well as the name of your points. Our next step now is to create the links and cylinders. So I'm going to close this. I can click OK. It will close the window for me, and I'm going to start creating the links. The first link that I'm going to create is link number 2, which is the crank. So I'm going to click on rigid body link like this. Now it says the length. We have the length for the crank is 10 centimeters. So I'm going to click on length because I would like to specify it. So I'm going to make this 10 centimeters. And I would like to keep the width and the depth for all the links the same. So I'm going to make width and the depth checked like this. Now the crank is connected between the origin right here and our point A. So So I will start the crank from the origin, click on the origin, and then drag until point A. As you can see, it created the link for me. Again, you will click on link, new part, define the dimensions, length, width, and depth. We'll select the location of the first marker at the origin right here, click on it, and then drag until you reach the second point. This will define the link for you. If you go under bodies, you will see we created part number 2. I'm going to change the name, so I'm going to call this link crank. So now I have the crank. There is 2 markers, marker 1 and marker 2 define the position of this marker, the position of this link. Let me zoom out on this area here. So I'm going to select zoom region, and I'm going to drag around my points like this. The second body that we would like to create is our connecting rod. So again, I'm going to use the link. Now the length is going to be 20. So I'm going to change the length 20. The width and the depth, I will leave them the same. The connecting rod starts from this point. So I'm going to click on this point, and it will extend to this point right here. This point B, I will click on it. Now you created part number 3. We are going to call it connecting rod. Rod. We will rename part 3, call it con rod. Con rod.
The link will start.
I will define it again. I will select link. The length is 20. Now I would like to define the connecting rod from point A. So you come close to the location of point A, you see Adams is highlighting that this is ground point A. Now I can click actually to select this location. If you extend the link now, as you can see, it gives you the exact length that we defined, 20 centimeters. So this second end is located at point B. So I'm going to go to point B right here. Now you can see point B is selected, so I'm going to click on this point. So now I have part 3. I need now to change the name, so I'm going to call it con rod. Con rod. Con rod. Connecting rod. So the last element, the third element that we are going to create is the piston, and we are going to create the piston out of a cylinder. So I'm going to click on this cylinder, and as you can see, it's asking for 2 things. Number 1, what is the length and what is the radius? So I'm going to select the length is 5 centimeters. This is actually, we are going to change this to 5 centimeters. We'll check on this box, and then we will add the radius also 5 centimeters. The location of the marker is this marker right here. So you will move your cursor until you come close to the marker. You can see Adams is picking the closest marker or the closest point to where you are located. So I'm going to click on ground point P. Now as you can see the cylinder. If you extend the cylinder in this direction, you can see the cylinder is moving with you. Okay? So this is our ground marker. Again, we will select the cylinder. We are going to select a new part. The cylinder radius, the cylinder length is 5 centimeters, and the radius is 5 centimeters. The marker, the base circle marker is M1. So I'm going to move to close to M1 and click on it. Now as you can see, the cylinder have been extended outward. So I'm going to click. As you can see, Adams created the cylinder for us. If you would like to see the shape in 3D, you can click on isometric. So you can see the cylinder is created like that. You can also toggle the shading, so you can see the shaded cylinder like this. This is exactly what we are looking for. So I'm going to toggle wireframe again, front view again. Now I'm going to change the name. I'm going to call this slider. And now we need to attach the specimen or the workpiece. So I'm going to select again another cylinder. So I'm going to click on the cylinder. As you remember, it has the same dimensions. Length is 5, radius is 5. The base cylinder is located at M2. So the base, the center of the base circle is located at M2. As you can see, when you move your cursor close to any point, Adams is going to give you the name of this point. So I'm going to move close to M2 and click on it. Once you click on it, you can see the cylinder have been created in this direction. So I'm going to click. You can see the cylinder have been created and along this axis. So I'm going to call this, change the name and call it workpiece. Before losing our work, it will be a good idea if we save our model. So I'm going to click on this diskette icon. So this will save our model. Do you want to save this database? Okay. Because this is our first time to save it. It's not going to ask us for our backup. We just would like to check if our model is correct. So we'll go to this simulation again. Click on the interactive simulation. I would like just to see 1 second of motion. What I expect is to see all the bodies moving at the same speed downward. If I run the animation, the simulation, Adams created the equations and solved them, and as you can see, all of them moved together. So the model is doing what we expected. I will return to the initial configuration and I'm closing my model, and then I would like to start building our joints. If you remember the joints we have between the crank and the ground, we have a revolute joint. Between the crank and the connecting rod, we have a revolute joint. Between the connecting rod and the piston, we have a revolute joint. Between the pistons and the specimen with the ground, we have prismatic joints. So we are going to build those joints together. In order to build the joints, I'm going to click on connectors and I'm going to select first the revolute joints. Click on the revolute joint here, second one from the top, and then as you can see, Adams is giving you the options. We're going to pick 2 points, 2 bodies, 1 location, because we know the bodies are in the same location right now. We're going to use the axis of rotation is normal to our grid. So now Adams is asking us pick the first body. The first body that I'm going to pick is the ground. So you can see the ground name is appearing here. So I'm going to click. I will move my cursor until I come closer to the crank. In this area we will have the crank and the connecting rod. As you can see, Adams is showing the name of the crank, so now I can click on the crank. We are going to create this joint at the origin here right now. So we're going to move close to the origin. It says crank marker 1. If you don't see crank marker 1, right click and it will give you list of the markers. As you can see, in this position we have the connecting rod center of mass and the crank marker 1. Actually I need this one, crank marker 1. So I'm going to click on it. As you can see, Adams created the joint for us, this icon, and this joint is attached to the ground. We can see that from the hatched lines. And you can see under connectors the joint name joint 1. If you would like to check if this joint is correct or not, you can look at the isometric view. You can see the hinge have been created, one side on the ground, the other side on the crank. So this joint looks good. So I'm going to change the name. What I usually do, I give the first body and then the second body. So this joint connecting ground to crank. So I'm going to call this ground underscore to ground. Ground to crank. I'm going to repeat it, so I'm going to delete this joint and create it again. I will go to connectors, select revolute joint. While going for this model, we are going to use two bodies, one location, normal to the grid. So now Adams is asking us, pick the first body, select the first body. So I'm going to move my cursor. You see Adams is showing the name of the ground. So I'm going to click on the ground. Now Adams is asking, select the second body. So I'm going to move close to the crank until I see the name of the crank. If you don't see the name of the body, right click close to it. So now as you see, Adams is telling you what are the bodies in this area. We have the crank and the connecting rod. I would like to connect the crank. So I'm going to pick it from here and click OK. Now as you can see, Adams is asking for the location. So I'm going to go to marker 1. In order to get exact marker, I can right click in the area. It will give me the name of the markers. So this is crank marker 1. I will choose it and click OK. As you can see, we have the joint created, and now it says joint 1. I'm going to rename it. I rename my convention of renaming. I start with the name of the joint by the first body. We selected ground, so it will be ground. And then the second body is crank. So now I know which bodies are attached by this joint. Now we are going to create the same process to create the revolute joint between crank and connecting rod. So I'm going to select revolute. Now I'm going to select the first body is the crank. So I will move my cursor. I don't see the name appearing. I will right click. So Adams is displaying which bodies are in this area. So I will select the crank. OK. And then the second body. I can see the connecting rod is not appearing. So again I'm going to click again. So I can see the con rod. OK. Now Adams is asking for the location. The location is actually located at point A. So now you can see marker A. So I'm going to click on this. It will generate the joint for me. And again, I'm going to change the name. I'm going to call this crank to con rod. So now I have the two joints. You can check the two joints are correct. So move the next joint. The next joint is actually a revolute joint between the connecting rod and the slider. So we'll select slider, and then we are going to go close to the connecting rod. Here is the name. I will click on it. Select the second body is this slider. Move close to the geometry. It will show the name. Click on it, and then the location is at the center of mass. So here is the center of mass. Oh, actually it's at ground B. This is very nice. So I'm going to select it at ground B. If you don't see the ground B, right click, you will see the name of the point here. So I'm going to click OK. Now the name of the joint, con rod to slider. In order to see if this joint have been created correctly or not, as you can see, the joint is hidden inside the cylinder. So it will be nice if I can hide the cylinder and see the joint and show the cylinder again. We can do that if we go to the slider. This is our body, this body here. This is the graphics that creates this body. I can right click and select hide. So you can see the cylinder have been hidden. Now you can also look at the 3D. You see the joint have been created here correctly. This is what we are looking for. So now our work is correct. So I'm going to show the cylinder again. I'll right click and select show. It will show the cylinder for us. So this is a very nice feature that you can show and hide graphics and parts as well. So now what will happen if we simulate the model right now? What happened actually, we have this part of our system have been attached, which means we are going to have some kind of triple pendulum. So this part should act as triple pendulum. How about this one? This one is not attached to anything, so it should fall down under the effect of gravity. So let's make sure that our model is working as we expect. Let's run a simple test. I will go to interactive simulation and see if the model is doing what we expect. Run. And this is what we can see. As you can see again, this is triple pendulum. The specimen is falling down under the effect of gravity. So now we think we are okay. Our model is going as we expect. So I'm going to work for the remaining joint. At this point, it will be a good idea to save your model. It's asking for backup. I don't need backup for more model right now. So in this model, we are going to start creating our prismatic joints between the specimen and the ground, and the slider and the ground. In order to create the revolute, the prismatic joint, we are going to click on connectors and select this third or this middle first row. It says translational joint. Now the translational joint is connecting two bodies at certain point, but it also defines the direction of translation, and the direction of translation must be clear to us. If you don't know, if you have something like inclined plane as the direction of translation, then you need to define a vector along this plane. Otherwise, your translational axis will be inclined, and it can cause the system will not be able to simulate. So here I'm going to create the prismatic joint between the slider, the specimen, and the ground first. I will click on this translational joint. Now the options that we have, because our model is assembled, we are going to use this option: two bodies, one location. Other options again, 2 bodies, 2 locations. And here we are going to pick the direction of the translation using geometry feature. Or you can select normal to the grid. Here it will be more appropriate to select the direction of the direction of translation from a geometry feature. We are going to pick the 2 bodies, 1 location, and then the direction of translation. How can we do this? We are going to select the first body is ground. As you can see the name of the ground here, so I can click. Now I'm going to select the specimen. So I will move close to the specimen or the workpiece. Now you can see the name of the workpiece. I will click on it. This workpiece is going to slide along the horizontal x-axis. So I'm going to select the location of this joint at the base right here, marker 2. And I would like the workpiece to slide along the x-axis. See, as you move close to any direction, Adams is picking a direction for the translation. We would like this specimen to translate horizontally, and we know this specimen is translating horizontally along the x-axis. So make sure this arrow is pointing along the x-axis and click. Once you click, you see this joint represents the prismatic joint. If you look at the joint, the model in the 3D isometric view, you can see the joint is aligned with the axis of the cylinder, and also it's aligned with the x-axis. So this is our prismatic joint. If you didn't select the direction correctly, you can look from the top. If the direction is not correct, then you will see this joint inclined along different directions. Make sure that the direction of the joint is correct, the way it's going to move, or the way it's expected to move. And now we're going to change the name. So I'm going to change the name, call it ground to workpiece. The last joint that we would like to create is another prismatic joint between the slider and the ground. So we'll repeat what we did before. I will click on prismatic joint, 2 bodies, 1 location. The first body is ground, so I'm going to click on ground. The second body is the slider, so I will move my cursor until I come close to the slider, and then I see the name, click on it. Now we are going also to attach the joint at the base of our cylinder, which is located at M1. So I will move my cursor close to this area. If you see the name, you can click. If you don't see the name of the marker or the point, right click. So you can see this list will give me what is in this area. I will select M1 and click OK. Now Adams is expecting again the direction of the joint. So I'm going to connect it to S1 because I know this is horizontal, so the vector is going to be horizontal. And again, the joint have been created. If I look from this direction, it looks horizontal. If I look from the top, you can see it's also horizontal. So now I am sure my joint is aligned with the direction that I need. I'm going to call it, rename it, ground to slider. And at this moment, we have completed our joints. Now, as you expect, we can check the motion of the mechanism. What I should have is a crank slider mechanism like this, and a sliding body. This mechanism can fall and move under the effect of gravity, but because this body will only translate along the x-axis, I should not see it moving at all. If I would like to check if my model is correct, I will go and check the simulation again. 1 second, 500 steps, that will be okay. So I'm going to run the simulation, and this is what we expected. The workpiece is not moving. The crank slider mechanism is rotating under the effect of gravity. The weight is grabbing the model to move, and this is what we wanted to see. One more thing that we need to look at, as you can see, when this body, the slider, is moving, it can interfere inside the other geometry. And this is something that we would like to prevent. We would like to create a contact between the two bodies. If this slider touches the workpiece, it will move with the slider. So now what we need to do is to add contact between the two bodies. Before doing anything else, let's save our model. I don't want to create a backup. Now our model is saved. So now let's add the contact between the slider and the specimen. How do we add the contact? We go to forces and select this. From special forces, we'll select this, create contact. So I'm going to click on this icon here. As you can see, it gives a name, contact 1. I'm going to change this to a contact, workpiece contact, workpiece underscore contact. Now it is asking for the two solids. The first solid, I'm going to select the slider. The second solid will be our workpiece. In order to select the first solid, right click, contact solid, and you can say pick. Pick, I will move to the close to the geometry. As you can see now, it says cylinder 8, slider cylinder 8. I will click on it, and then J solid, I will right click again, pick. I'm going to this cylinder. It says workpiece cylinder 9. So I will click OK. I will leave all the other parameters for now as is, and I will click OK. As you can see, the contact force have been created under forces, as you can see. Now if I run the simulation, I will expect that this cylinder is going to hit this cylinder. So this cylinder is going to move in this direction without a stop, while this is going to continue oscillation. To see that, I'm going to click on simulation, run, and this is what we have. And as we expected, as you can see, the piston pushed the workpiece. The workpiece has no friction, so it will continue to move, while the the slider is going to move back to the initial condition. This is what we expected. So it seems like our model is working fine. I will click on the diskette to save it. No backup. So our next step now is to connect the spring, which is actually connected between the center of this workpiece and S1. The spring is a force, so we'll go under forces and we'll select this linear spring. Adams allows you to model torsional spring or linear spring. So if I click on this linear spring, you can specify the stiffness and damping of your spring. So I'm going to specify the stiffness and damping. Now I'm going to select the 10 and 1. What is 10? The units of the stiffness is usually Newton meter, Newton per meter. But because we are using, for the length, we are using millimeter, so this stiffness is going to be Newton per millimeter. So now K is equivalent to 10 kilonewton per meter. And the same here, 1 Newton per millimeter per second. So this will be equivalent to 1 kilonewton per meter per second. So now I specified the stiffness and damping. Now Adams is asking you, where are you going to connect it? I'm going to connect it from this center, the workpiece center of mass. So you move your cursor until you see the name of the marker, workpiece center of mass. If you don't see the name, right click. It will give you all the objects in this area. So I will find workpiece center of mass. I will click OK. Now Adams is asking for the second point. As you can see, it is showing you where it is picking right now. I am connecting it at this S1. So I will move my cursor until I come close to S1 and click. As you can see, Adams created the spring for us. Now our model is almost complete. So I'm going to click Save. Now if I run the simulation, what I expect is that this piston, when the slider hit this workpiece, try to push it, the spring is going to resist the motion and it may not move because the spring is stiff, and I will expect the slider to go back on the other direction again. So let's see if the simulation is correct. Now the slider is moving, contact, small motion, is not able to push it anymore, so it will just stop like this. Now from this simulation I can expect that I have high damping. In this system I expect that I have high damping. So what can I do in order to reduce the damping? I can go to the spring and edit the data of this spring. In order to change the data, I will right click on the spring, select modify. This is how can we change the information about our spring. I'm going to make the damping coefficient, instead of 1, I'm going to make it 0.1, 0.5, and click OK. Now let's see how it will work. Yeah, now it is oscillating a little bit, which is acceptable now. So now it stopped, almost stopped. No more motion. This is what we expect. Now, how the crank slider is going to make a complete rotation? In order to have a complete rotations and the continuous operations, we need to add a motor to drive this crank slider mechanism. How do we add a motor? In our first design here, we are going to add motion, input motion. So I'm going to reset my model and I'm going to define the motion to act on the joint of the crank. We would like to add the driver that is going to drive this mechanism continuously. This is what we called it before, motion input. So how do we generate this motion input? We go to motion right here. Under motion you will see that you have linear motion, translational motion, or revolute or rotational motion. So now we are going to click on this rotational motion. Here it says the rotational speed. This defines the rotational speed. Rotational speed is defined by the angles in second. So this says 30. 30 what? 30 angle. Oh, what do you mean by angle? What is the units that you have? If you remember, when we defined the units in Adams, we defined our units in degrees. So this 30 means it's going to rotate 30 degrees per second. If you want to make sure of the units, you can go to settings, click on units, you will see which units are used. The angle is degrees. So now what I'm going to do, I'm going to make it to rotate 1 cycle per second. Oh, what do you mean by 1 cycle per second? I would like this mechanism to complete 1 rotation in 1 second. So what will be the speed? 1 cycle is 360 degrees. So I need to change this to 360. So I'm going to change 360. So this will be our rotational speed of our mechanism, 360 degrees per second. Now, I would like to define which joint we are going to move. If you move your cursor, Adams is going to pick only the revolute joints. So here we have the ground to crank. Here we have the crank to connecting rod. Here we have the connecting rod to slider. But also we have the sliding joint. Adams is not picking it. Also here, Adams is not picking it, because Adams is going to help you to select the correct joint type. So now it is showing which joints you can select. We are going to derive this joint, ground to crank. So I will move until I see the name of the joint. If you see the name of the joint that you are driving, you can click on it. If you have a lot of joints in the same area and you don't see the name of your joint, you can right click. Adams is going to give you list of the joints here. You can select the one that we are looking for and click OK. Oh, see now, instead of having a small arrow for the revolute joint, now we have this big arrow for the driven motion. And then also see, we have created a new item. So you can see motion is created. Motion 1. Usually it will be a good idea to define every element with a name. So this will be crank driver. I'm going to rename it as crank driver or crank motor. Also the spring, I'm going to call the name of the spring as workpiece resistance. Workpiece resistance. So now if I run this simulation, what I should expect is that this crank is going to rotate 1 full cycle every second. So go to simulation, under the interactive simulation, click on active simulation. I'm going to run it for 2 seconds, and I'm going to use 1,000 steps. Now what is going to happen? We should see the crank rotating. When the piston or the slider touches the workpiece, it will push it down until it reaches the maximum center, and then it will start rotating. This workpiece will start coming back under the effect of the spring. So I will run the simulation. So now we have the contact. Now as you can see, Adams is pushing the workpiece until the end, and then it will start going back on the other direction. until they lose the contact. And now the second cycle, it will do exactly the same. And at the end, as you can see, atoms should stop. Two complete cycles, every cycle in 2 seconds, atoms moved the crank 360 degrees. For 2 seconds, it moved 2 cycles. Now, I can see that my simulation have achieved my goal, so I'm going to save my model without backup. So now I have our simulation saved. Let's monitor our simulation behavior. What we would like to do is to look at the force in the spring. So in order to look at the force in the spring, I can right click on the spring. You can see the spring name appeared. I'm going to select a measure. Now what do we want to measure? I would like to measure the spring force. So here is the measure name. I'm going to call this measure name. I will call it spring underscore force. And the object is this workpiece resistance. This is okay, this is what we want. And I would like to look at the characteristic. From here I would like to look at the force. You can see the deformation, the velocity, or the force. So I'm going to see the force. If I click OK, it should show or display this strip of our contact force. The spring force. Now, what we expected and what we see. The spring force is going to start from 0 because there is no force acting on the spring. When the slider started touching the workpiece at this time, the contact force is going to push the workpiece backward, and this will start creating a resistance force in our spring. It will continue to increase until the spring reaches its maximum deflection. Once the spring reaches the maximum deflection, and this will be close to the end of the cycle of our piston, now what is going to happen? The piston will start to retract, going back. So the contact force between the spring and the spring is going to push our workpiece against the slider, maintaining the contact force, but at the same time, because the deformation of the spring is decreasing, the spring force will also decrease. The contact force is creating this noise, so we don't see very good smooth resistance force. The contact will continue until the spring reaches the undeformed position, while the piston is moving backward. Once they lose the contact, the spring force will become 0. And then this will be the end of the first cycle. Because the cycle is going for 2 seconds. After 1 second, it will repeat again, and we should get similar force like this. This noise in our force is coming because of the contact. And this indicates that the contact doesn't have sufficient damping. So in order to improve this simulation results, I can improve the damping in the contact force. So in order to do this, I will right click on the workpiece contact, right click, select modify. The damping in the contact is only 10. I'm going to make this 50 and click OK. Now I will run the simulation again and see how this will impact the quality of the forces. you can see it's moving. Now the contact started, the spring is deforming, the force in the spring is rising, and as you can see it's getting much smoother than it was before. Now once it starts to retract, the contact force is decreasing until they become right here, no more contact, so the spring force is equal to 0. And now the piston is going to continue for the second cycle. Contact will start again, and as you can see the spring force is increasing. As you can see, the contact force right now is much better than, or the spring force is much smoother than before. We still have some irregularities, but this is acceptable and this is okay because of the stiffness is pushing against our contact. And now the simulation is complete. Our model, I'm going to save this simulation model with no backup. If we think about this model, the model was initially at rest, and suddenly we told this model to change the speed from 0 to the defined speed, 360 degrees per second. And this usually is a non-realistic change in the speed. If you look at the speed, if you look at a plot of your speed, you will see something like this. You have, if this is the time, and this is the value of the speed. At time equal to 0, the speed will change from 0 to a very high value in no time. This would require significant power that would be very difficult to find. So we can call this change is a non-realistic change. Where is this can happen? Actually, this is what we did when we applied the driver. So if you look at the motion right here, if you right click on the motion and select modify, this is very nice window that we use it to define our motion. So what happened? This is our name of the motion. This is our joint that we are driving, the type of rotation, the type of motion which is rotational, and we are going to define this rotation as a function of time. How does this function of time look like? Oh, it depends on what we are driving. We are driving the displacement. We said make this displacement to change with constant velocity. If we have a constant velocity, this means the displacement will be equal to 360 multiplied by the time. So this is exactly what we are looking for. We are looking for angular velocity, constant angular velocity. So the angle is going to change using this function, linear function. You can also specify the velocity. You can ask Adams to define the velocity or the acceleration if needed. So here we are defining constant velocity to define the displacement. It's a linear function of time. If you change this to control the velocity, in that case you don't need the time. If you have constant acceleration, you can change the values here. But for now we have the displacement. We are controlling the displacement. If you specify the velocity, then you need to specify the initial value for the displacement, because this is kind of differential equation. You specify the velocity, then you need the initial condition for the displacement. If you specify the acceleration, then you need the initial displacement and the initial velocity. So now let's assume we are going to have control the constant velocity with initial displacement 0, like this. What will happen to this equation? This equation should be changed now, because this will not make constant velocity. This is going to make the velocity changing with time. How do I change this function? You can edit from here, or you can use a function builder. So if you click on those three periods, it's going to open what we call it function builder. What is function builder? It allows you to build a very complicated equations if needed, using the tools and the mathematical functions that you have in MATLAB, in Adams. Once you build your function here, you can check how does this function looks like. So how do we check the function? You can click on this plot. If you see this plot, you can see it's changing function of time like this. So if I would like to change this, make it constant, I can just edit this, delete the time, and make it constant. So what I would like to do now is actually to delete this time. If I delete this time, I will just get a constant value. I can check using a plot, it's a constant value. But this constant value, actually Adams converted it into radian per second. So you can see this will be 2 pi. 360 will be 2 pi. Now, we are satisfied with this value, so I'm going to click OK. So now I have the velocity is defined by this constant value. What I should expect now, if I click OK and run the simulation, I should get exactly the same behavior as I had before. So if I run this simulation, no changes should have happened. We don't have contact, we don't have force in the spring. Once the contact started, the force started, as you can see, it's moving. I know it is moving the same ways. I don't need the update graphics. So it runs the simulation. Now it completed our simulation. Now as you can see, it has exactly the same behavior. But what is the problem with this model that we have created? The problem mainly is in our input force. This input force is extremely large, or the required power will be extremely large at the beginning due to this sharp change. So instead of dealing with our input to have something like this, what we usually do is to create what we call it a step function like this. So what is a step function? The step function allows you to have a smooth transition between two values. So instead of jumping from 0 to this high value in no time, what we are trying to do is to make this transition smooth like this. When we have this smooth transition, this is going to make the change in the velocities and the acceleration smooth. The forces will not be as high as it would be when we use this simple case. So how do we do this? There is a mathematical function in MATLAB that allows us to use this function. We call it a step. This step function will define the change in the speed as a function of certain variable. The variable that we'll have is our time. So the x-axis is the time. We are going to tell Adams to start changing the speed from 0 to this high value such that it will start smooth at time equal to 0 with 0 velocity, and then it will ramp the velocity up until it reaches the maximum value at this time. We can have control about this period such that it becomes smooth like this. For example, I can say at time equal to 0, the velocity is 0, but at time equal to 1 second, the velocity reaches the maximum value. How I can do that? I can do this in atoms by changing the value of the velocity. So I will go to the velocity here, crank motor, right click, and choose modify. Over here, this is our function. So I'm going to change this. I will click on the function builder. Now I would like to change this constant value. So I'm going to delete it. And I'm going to select mathematical function called step. Oh, what mathematical function? As you can see here, those are the functions that you can use. You can use all those mathematical functions. If you would like to have sine inverse, absolute value, cosine inverse, cosine, exponential cosine, exponential function, log function, minimum, maximum, sine, tan, all of those mathematical functions, you can utilize them to define what you are looking for. So here I'm going to select this step function. Once you select any function, Atoms is displaying help right here. So this says we are going to create a step function that is function of certain independent variable. In this case, they call it x. And then you will need the initial value of this x and the value of the parameter, which in our case is the velocity at this initial value. So if we look at our parameter here, at time equal to 0, the velocity is 0. At time equal to t1, the velocity is maximum. So in our case, I can define those parameters here. So now, in order to utilize this function, I double click on it. Now, I will replace every one of those x's by the corresponding value. So I will tell Adams that I'm going to use the independent variable is time. So I will specify time here. The initial time that I would like to change the value is 0. And the value of the velocity at this time is also 0. I would like to increase our time, the velocity, in 1 second. So x1 will be 1 second, and the maximum value will reach 360 degrees. So I will click change this value. If you would like to see how this function will look like, you can click on plot. It will create the plot like this. So now you can see from the time here is it changing. The value of our speed is going to change from 0 to 2 pi. And this is exactly what we are looking for. We are satisfied with this, so I'm going to click OK. This will copy the function over here. So now you can see the functions that we created. I'm going to click OK. Now I'm going to run the simulation, and this is going to complete the simulation. Let me run it with graphics update. So you can see the motion. The motion starts with very slow. As you can see, starts very slow, and then it will increase the speed. So as the time increases, you can see the time is here. As the time is increasing, the piston will move faster. And as it approaches the workpiece, it's going to create the contact. The contact is going to increase our force in the spring. So now you can see the force in the spring is increasing, and then it will reach the maximum value and start retracting. After 1 second, the rotational speed of our crank will reach the maximum value, and as you can see, it will continue continuous rotation if you wish, based on the simulation. This will be almost the end of this presentation for today.